Okay, thanks everyone for coming tonight. I'm Ramona. I'm a founding engineer at Kumu. I'm very happy to welcome here for the event, Future of Relational Foundation Models. Yeah, as I said, I work for Kumu. We are sponsoring this event. Vanya, unfortunately, who planned to come to Berlin, isn't able. He canceled his trip last minute, but I'm very excited about the lineup we have today. We have first speaker sessions, like 3 different talks, and then after that, there will be like time for food and networking and discussions in smaller group. First, we start with Q. He talks about tabular foundation models, and he's also the creator of TabICL. And then Matthias takes over and speaks about like relational models on relational databases. And he is leading the research team at Kumu. And then Miha is taking over and speak about how to apply those machine learning systems to large-scale data sets. And he is an ML infra engineer at Kumu. As said already, I think the sessions will take around up to like 7:45, and then there will be food until 9. We have this location until 9. We are also hiring at Kumu, so if you're interested in jobs, there are a couple of people around. We all have our names written in red, so you can just approach us on like which open positions do we have. We do have those stands with QR codes, both on open positions, and you can directly upload your resume. In case anyone wants to smoke, please go outside, and also for networking later, we can use this like small terrace and go outside. Also, we're taking photos tonight, so if you don't want to be on any like public photo, please approach me or Katie, and then we will make sure to account for that. I think I mentioned everything. So yeah, I already mentioned the agenda. I think I will directly hand over to Q for starting with tabular foundation models. Yes.
Okay, hello everyone. Yeah, hello everyone. My name is Jing Gang. I'm so happy to be here to give a talk about my work, especially typical series. And today I'll be presenting typical V2, a better, faster, scalable, and open tabular function model. Currently, I'm a postdoc at INRIA Saclay, and this is a joint work with David, Gael, and Martin. And this is the roadmap for my presentation. First, I will introduce some background about tabular learning and why is it challenging. The next is tabular foundation model, and the core of this talk is typical V2 itself. And finally, we will discuss some feature directions and open problems. Tabular data is ubiquitous, and it is basically the most dominant data format across industry, healthcare, finance, and the scientific domain. And the data organized into rows and columns falls into this umbrella. However, tabular data is inherently different from other modalities. For example, natural language processing or computer vision, because in NLP, we have sequential tokens with clear positional correlations. In fact, in computer vision, we have grid structured pixels with spatial locality. However, for tabular data, there is no natural ordering among features. And the features are generally heterogeneous, mixing numerical values, categorical labels, and sometimes even contextual content. In addition, the semantic of each feature change completely from one dataset to the other. So this absence of shared structure is what makes tabular learning so challenging, and why architectures like Excel in other domains cannot be simply translated to the tabular setting. In fact, before tabular foundation models, the tree-based models such as XGBoost or CatBoost dominated the tabular learning. In fact, a paper from our team pinpointed 3 reasons. First, neural networks are biased toward smooth functions. However, tubular targets are generally irregular. Second, tree-based models are robust to uninformative features. However, neural networks are not. The last one is that, in fact, as I mentioned, each feature in a table carries its own semantic meaning. So the original feature axes matter. However, neural networks are rotationally invariant and lose this axis-aligned structure. So these findings set the stage for a new learning paradigm we call in-context learning and tabular foundation model. So I have to say that the field of tabular foundation models has been evolving rapidly. Starting from, in fact, TAP-TFN from 2022, a paper from Freiburg University, we already seen a wave of new models. For example, TAP-TMV2 from Paralab, typical from our team, relational foundation model from Kumo, Limix from Stable AI, a Chinese startup, and Metro from Amazon, and Nextures from Fundamental, and our latest typical V2. So, however, I have to say an important trend, like most of these models are not fully open source, especially when it comes to pre-training code and data. However, our typical V1 and typical V2 are completely fully open source, which we believe is very important, in fact, for the community progress. The key pattern underlying these models is in-context learning. On the left, a large language model can learn the pattern from the prompt and can unscramble a new word. In fact, for a new query example without training and parameter updates. On the right, we have a tabular analog. In fact, given a table with input features and targets as in context, a tabular foundation model can infer the underlying input-output relationship and make a prediction for a new query example that is a single text sample. So, in fact, the pattern is the same for these two examples. That is, in-context learning can learn the pattern from given examples without task-specific adaptation or fine-tuning. This is what makes tabular foundation model so powerful, because we can use a single model to deal with any data set under reasonable time. What I mean, fast predictions. So, sorry, there is something wrong for these two parts, but you can just look at, in fact, the architecture. So now I just want to describe two mainstream architectures for tabular foundation models. The first one is TAP-PFV2. TAP-PFV2 has adopted a kind of cell-based design where each cell gets its own representation. It then uses the dual attention, alternating between columns-wise and row-wise attentions, which enables inter-row and intersample, intersample and interfeature correlations. In fact, to lower the computational cost to some extent, TAP-PMV2 will group some features and embed them together, which can just reduce, in fact, the number of effective features or the effective dimensionality. Another one is that, in fact, for TAP-PMV2 will inject the target earlier as an auxiliary column. In fact, they just concatenate, in fact, the input features and the target together as a whole table. However, the big challenge of TAP-PMV2 is that it has a complexity of m times n squared plus n times m squared, where n is the number of rows and m is the number of features. And it can easily, in fact, become a bottleneck in both memory and compute when the data to handle grows largely. The second one is TAP-SL. In fact, we call it typical, accepted at ECML of last year. Typical uses a fundamentally different approach, compressed than in-context learning. So what I mean is that, in fact, first, each feature will be processed individually using a set transformer. This set transformer has a linear complexity with a number of rows for feature embedding. And then we perform, in fact, the interfeature interaction will comprise each row into a fixed dimensional representation. And finally, in-class learning operates on this compressed representation for the final prediction and inference. And typical has a complexity of n times m squared plus n squared. So importantly, the final in-context learning, the cost of the final in-context learning only depends on the number of rows instead of number of features, making it more scalable over the feature dimension. And its next generation typical V2 also builds on this architecture to keep the same efficiency profile. Most of tabular foundation models are pre-trained on synthetic data instead of real-world data set. This is very different from larger models or computer vision models. So, in fact, the idea is very simple. First, we will generate a directed acyclic graph, and then we will sample values for the root nodes. Next, we propagate values, in fact, through the graph via some mapping functions over edges. And eventually, in fact, we just choose some nodes as the input features and another one as the target. So currently, the main difference across different synthetic data approaches lie in two things. The first is graph topology, and the second one is the mapping functions. In fact, tabular foundation models are already beyond purely classification and regression. And currently, tabular foundation models are becoming versatile building blocks beyond the standard, for example, classification and regression, including graph learning, time series forecasting, and causal inference, and many other downstream tasks. In fact, this breadth of applications demonstrates the potential of tabular foundation models as a general purpose tool for structured data. However, there are some challenges in the current landscape of tabular foundation models. So the first one is that, in fact, most of models are becoming increasingly closed source. The second one is that, in fact, models are becoming bigger and bigger. In fact, scaling improves the performance, but at the steep computational cost. And the third one is that, in fact, most of the models have limited scalability, and they struggle with data sets, for example, beyond 10,000 or 50,000 samples and beyond 500 features. So our goal with typical V2 is very clear. In fact, we just want to build an open source, state-of-the-art, fast, and scalable tabular foundation model so that the community can build upon. And before that, I just want to outline, in fact, some key limitations of our previous model, typical V1, that motivate the development of its next generation typical V2. The first one is representation collapse. In fact, as I mentioned before, in fact, for typical V1, each feature is processed individually. So in the case where for the features with similar distributions, in fact, they will get nearly identical embeddings. The second one is that, in fact, typical V1 prior is still not very good. In fact, it lacks some diversity. The third one is long context generation. Typical V1 is poor in long context generation. The last one is that typical V1 only supports classification with no regression capacity. So our new model, typical V2, aims to address these limitations. This is the architecture of typical V2 with its three key architectural innovations. The first one is repeated feature grouping. In fact, as I mentioned before, typical V1 processes each feature individually, so causing representation collapse. In fact, in type of PFM2, it mitigates this problem by grouping multiple features into a single token. But it comes at a cost of reducing the number of effective features and losing fine-grained information. So in fact, in typical V2, each feature is still embedded together with other two features as a group of three. But we perform circular shift so that each feature can appear into different groups, and each time paired with its two neighbors. So in this case, in this way, in fact, we alleviate representation collapse while keeping the same number of features. The second one is target-aware embedding. So in typical V2, we just use, in fact, inject the target earlier during the embedding process. This helps in two ways. The first is that, in fact, it will enriches, in fact, the feature embedding context. The second one is that it also helps distinguish features with similar distribution, but a different relationship with the target. And the last one is query-aware scalable softmax. And we develop it to enable, in fact, the inference on longer context than that seen during pre-training. It is very useful, and I will explain it in detail over the next 2 slides. So, in fact, first I want to give you some background about scalable softmax. The problem is attention fading. So, what is attention fading? So, in fact, as context length grows, the softmax denominator, in fact, will just increase because softmax cannot yield zero result. So, meaning that, in fact, as the context length grows, meaning that we will have more useless information. However, and this useless information will accumulate. And the consequence is that, in fact, the attention weight will tend to become uniform, so that the model cannot retrieve or focus on the most relevant part. And in the paper of a scalable softmax, the author just introduced some learnable, in fact, rescaling factors to softmax logics. And the author just found an interesting observation. That is, these learned factors exhibit a clear logarithmic relationship with the context length. So, and motivated by this observation, the author, in fact, proposed a simple yet effective temperature scaling technique for attention, which is exactly scalable softmax SSMax. So it just scale, in fact, the temperature, in fact, the softmax logics with a factor proportional to the logarithm of the context length. So it is, in fact, it can effectively compensate for the growing denominator as the context length grows. And for the concrete implementation, it is quite easy. So we can just, in fact, multiply the query with the scaling factor without changing anything inside the attention itself, so that we can just make use of the efficient implementation, especially flash attention. It is very useful. However, scalable softmax use a scaler to scale all dimension equally, and we want to improve it by introducing query-aware scalable softmax. The first part is beta scaling. So what we did is that we use an MLP taking the logarithm of the context length log n as input to produce a vector, generalizing the scalar scaling to element-wise per dimension scaling. The second one is query-aware gating. We use a separate MLP taking each query as input to generate a gating signal, making the scaling content-aware and query dependent. The last one, in fact, the query, the base scaling, and the gating signal are combined via element-wise multiplication. So concretely, the query-aware scalable softmax is used in the set transformer during the columnar embedding, as well as the final in-context learning transformer. In fact, to understand and demonstrate the effectiveness of query-aware scalable softmax in attention fading, we design a needle in haystack problem. In fact, which is just a multi-class classification problem. In fact, if you look at the paper on the right, there is a white triangle, which is an anchor example. So at the same time, there are also 4 negative clusters. So the basic idea is that, in fact, we want to correctly predict text samples that are closest to the anchor sample, while increasing the negative samples. So in fact, we can say that, in fact, for the standard attention without a scalable softmax, as we increase the number of negative samples, we can say that, in fact, the decision boundary of the anchor sample shrinks largely. It basically collapses. However, for the query-aware scalable softmax, we can see that, in fact, the decision boundary of the anchor sample is still relatively robust and can contain all test samples, even though the the negative samples has reached 50,000. Not like there is only a single anchor sample that is useful, in fact, for the prediction in the training set. So this result is very interesting and impressive to demonstrate, in fact, the effectiveness of query-aware scalable softmax in attention feeding. This figure represents, in fact, is a high-level structure of our synthetic data prior generation pipeline. So, in fact, we made some improvements. The first one is about, in fact, the graph diversity. In fact, we generate diverse graph topologies, dense graph, sparse graph, scale-free network, etc. And then the next one is like, in fact, we significantly expand mapping functions. In fact, as you can see, there are MLP tree-based models, discretize, etc. And the second one is that following type PMV2. In fact, in this graph, each node represents a vector instead of a scalar. If you look at the paper of the Nature paper of type PMV2, in fact, they've already adopted this one. And we found this is very useful, in fact, to have a richer embedding representations. And the last one is that, in fact, we will filter out unpredictable data sets to ensure the quality of pre-training synthetic data. This figure is the visualization of some classification synthetic data sets. In fact, we can see that the boundary decision boundaries are quite diverse. Notably, we can find that, in fact, there are some data sets has already shown access aligned decision boundaries. So this is very important, in fact, to incorporate some inductive biases of tree-based models during pre-training, because we know that, in fact, tree-based models are still very useful, in fact, for turbo learning. So we want to incorporate it. So overall, our synthetic data prior has already covered a wide range of data geometries. For the pre-training, in fact, we just adopt the same strategy as typical V1, which is basically a three-stage coverage learning that gradually increase the number of samples up to 60,000. However, the number of features is always no greater than 100. In fact, another big change is that we use the Moore optimizer to replace the Adam optimizer. In fact, this slide just compares, in fact, the Adam W optimizer and the Moore optimizer. A big difference is that, in fact, the Moore optimizer will just perform Newton-Schultz orthogonalization to orthogonalize the gradient matrix. So intuitively, the Moore optimizer will just, in fact, ensure that the update will have the equal norm across all singular directions. So that no direction is disproportionately large and small. In fact, this can just lead to efficient optimization. In practice, in fact, by using the Moore optimizer, we can achieve both faster convergence and final better performance. This is very useful. This figure represents our ablation studies. In fact, the key findings is that the biggest gains are from our new prior, from the query-aware scalable softmax, from the target-aware embedding, and the use of the Moore optimizer. And another finding is observation is that we found we need to improve both the architecture and the prior data to have a better performance. If we only improve one of them, the performance gain is not very obvious. So we need to improve all of them, both the prior data as well as the architecture. In fact, for another one is very different is that we use the quantile-based, in fact, prediction for the regression task. Concretely, the model will predict 999 quantile levels, in fact, and which is trained using the quantile loss or pinball loss. So, so for the point estimation, we just average over all predict quantiles. And for the probabilistic modeling, what we did is that, in fact, we first fixed the quantile crossing, which is a common problem, in fact, for the quantile prediction. Then we will extrapolate, in fact, it with the tails with exponential models, so that it can just model the whole distribution instead of just a truncated distribution. And we found that, in fact, our approach is better than the standard mean squared pre-training, as well as the beam-based discretized approach used by type PMV2. Because for type PMV2, in fact, they will just discretize, in fact, the target into different beams, and just convert a regression problem into a classification problem. And our approach is better than type PMV2 approach, at least using our own syntactic data prior. Okay, it's the time for the performance. So yeah, this is, first of all, we've already achieved the soda performance on the Tab Arena benchmark, which is currently one commonly used, in fact, benchmark for turbo learning. On the y-axis, it is improvability, which measures, in fact, a relative gap to the best method across each data set. So we can see that typical V2 achieve the best trade-off between compute and inference time. So and the performance, meaning that it just in fact, pushes the parallel frontier of top-level foundation models. On the right, yeah, in fact, there is a new thing about this one. In fact, just this morning, Prior Lab has just released their new minor improvement, type PFN 2.6. And the typical V2 is still better than type PFN 2.6. Yeah, Prior Lab just released this new model this morning. However, I didn't put it, in fact, on the figure. Yeah, again, in fact, Talent has achieved the best performance on another benchmark, commonly used benchmark, which is called Talent benchmark. It has more data sets, a total of 300 data sets, including 200 classification data sets and 100 regression data sets. And we can see that, in fact, typical V2 is still the best one. Yeah, in fact, the inference speed is very important for real-world applications. And in this figure, in fact, we just compare typical V2 and type PFN 2.5 across different hardware. And we found that, in fact, typical V2 is largely faster than type PFN 2.5, especially on CPU. And in fact, we are really proud of it because you can just use typical V2 on your laptop, even without GPU, or even on your MacBook. In fact, it is generally fast. So meaning that this is also one of our goals, that we just want to develop a model that can run locally instead of just using GPU. We also want it to work, in fact, for CPU or even your MacBook on Apple Silicon CPU. Scalability is another advantage of typical V2. In fact, on the left, we show the top ranking with respect to the number of samples. In fact, in the Talent benchmark, we can see that, in fact, typical V2 works quite well, in fact, across all scales. And on the right, we also evaluate typical V2 on two huge data sets with more than 500,000 samples. And we can see that typical V2 is still very competitive. So in fact, meaning that, in fact, we largely address one of the biggest limitations of top-level foundation models, that is limited scalability. And I have to say that, in fact, our new query of very scalable softmax and curriculum learning or pre-training made a great contribution to this excellent scalability. Yeah, I just want to show you the versatile use of top-level foundation models, especially for typical V2. So typical V2 can be used, in fact, for zero-shot time series forecasting. And the basic idea is that, in fact, for each time series, we can just convert each time step, in fact, as a row of a table. And we just use temporal features, in fact, as columns. And in this case, in fact, each time series, what I mean is univariant time series forecasting is just convert to a regression problem. So that typical V2 can just solve it. And it works quite well, in fact. Another one is about unsupervised learning. So in fact, typical V2 can also be used for some unsupervised learning tasks. For example, for density estimation, outlier detection, and even data generation. So the idea is that just to decompose the joint distribution using the chain of the probability. So that each conditional will be a regression or classification problem that typical V2 can will solve. Because for regression, in fact, we use content-based prediction, which is essentially a probabilistic model. And for the classification, we directly output the probabilities, which is also, in fact, a probabilistic model. So meaning that we can do very cool things like unsupervised learning tasks. So what is next? So in fact, the first one is about multiple or relational learning. I think after me, I think the relational foundation model of Kumo has largely solved this problem. And then the next one is multimodal tubular foundation model. Yeah. So in addition, we need to care about, for example, causal inference and generative modeling instead of just, in fact, regression or classification. The next one is faster inference because tabular foundation models are still quite slow. If we only compare inference time or inference speed, compare tree-based models. So, and this will largely hinder, in fact, some real-time applications. For example, real-time outlier detection. It is basically infeasible, in fact, if you use tabular foundation models. But tabular foundation models are good at continual learning because you can just update, in fact, your in context on the streaming data. However, it is quite slow to run. So meaning that we still have to improve the tabular foundation models for faster inference. And the next one is about structured and unstructured data. Because in fact, we already observed that, in fact, for example, many large models has already output structured data, especially in the agentic things. So because structured data is easy to retrieve, manage, and compare. So what means that there will be more and more applications of structured data. And in this case, how should tabular foundation model adapt to this change? Okay, 5 more feature directions. The first one is about efficient tabular attention. Because in fact, if you look at TabPFN V2 or typical, we just perform, in fact, the full attention over all samples and over all rows. However, it will just hinder the scalability if you want to deal with very large data sets. So what it means that, in fact, we need to design a kind of a smarter or more intelligent attention that can achieve a kind of adaptive compression. In fact, during the forward path, so that we can achieve a better scalability. And the next one is about the agentic things. In fact, how should we combine large models and tabular foundation models for a better agentic workflow for structured data? And the next is better prayer, in fact, for to reflect the complexity of real world, especially for causal mechanisms and temporal dependencies. The next one is about, in fact, we need to better understand in context learning, why it works and why tabular foundation models are so powerful, so that we can just introduce some pretty simple innovations in both architecture and pre-training. The next one is, the last one is about the scaling law. In fact, currently there is no, there is a paper which is called TabDPT, but it is pre-trained on real world data. What means that there is no, in fact, a paper that conducted extensive experiments to show the scaling law for tabular foundation models. Yeah, in fact, I think this image is very popular very recently from the NVIDIA GTC conference. So in fact, because many startups use it, in fact, to justify their existence and justify, in fact, the potential of structured data. But no matter how this image is used, the fact that Jensen Huang used this mentioned structured data at the very beginning of keynote has already demonstrated the potential of structured data. So I think the future for structured is very exciting. Thanks for your attention. If you have any question or if you would like to collaborate on something, you can just contact me. Thanks.
Do we have time for a few questions? Does anyone have questions?
Thank you for talking with me. With respect to future directions, what are your thoughts on incorporating some world knowledge into these models? Like if you can combine them in some way with the world knowledge that you have in the Netherlands or
In fact, I think this is a very important direction because currently, especially for example, for many foundation models, they do not have world knowledge, especially for causal inference. And this is one of the very hard direction. They called world models. For example, Yan LeShuang just have a new startup working on its own world model. This is very important, and I think it is also related to causal inference. So meaning like how should we design a better, for example, tabular synthetic data pair. But I have to say that I do not have a clear mind currently. But I know it is very important, but I don't know how to achieve it. Maybe we need to use another foundation model. For example, the world model from Yan, the JAPA or something else. But it is very important to make the model be aware of the physical world. This is very important, but I have no idea how to achieve it.
Any other questions?
Sorry, I joined a bit late, so I don't know whether you have covered it or not. You also talked about time series prediction.
Okay. Yes, this one?
Yeah, so I'm currently using time seven from Google. So
okay.
how this compared to that?
Yeah. In fact, in this slide, I just want to show typical or tabular foundation model is versatile for other applications. But what you just mentioned, for example, TEM-FM is one of the popular or a pioneer work in fact in time series foundation models. But these foundation models are, in fact, for example, TMF or these time series foundation models are specifically for time series because, for example, they will just at the beginning because their pre-training or the architectural design are basically for time series. So meaning that they will have some positional correlations. For example, you can use rotary position coding, etc. However, in fact, here these models, for example, typical V2, is designed for tubular learning. At the beginning, there is no temporal information. But what we want to show here is that tabular foundation models can just be used for time series forecasting. But they are different. Because typical V2 is for tabular data at the very beginning. But for what you just mentioned, for example, Google's TMTF is designed and pre-trained for time series at the very beginning. Yeah, they are different. Thanks.
Any other questions?
Yeah.
On how many data sets was the model trained, pre-trained?
A very good question. I don't know if I already mentioned, write something. No, nothing. If I remember correctly, we've already used 7 million statistical data sets in total, which is smaller than that of our typical V1 and typical PFM2. Yeah.
And how did you select these numbers? How did you come up with the 7 million? Was there any?
No, in fact, the pre-training unit is not number of data sets. It is, for example, a number of steps or the batch size, other designs. But what means that after our 3 pre-training stages, we found that we just use basically around 7 million data sets. Yeah. This is not mean that 7 million data sets are enough, in fact, for the performance, or even larger number of data sets can give you better performance. I'm not sure, to be honest.
There's one more question.
Like in omics, tabular omics, you have very few samples. Do you have any comments if somebody uses few shot learning, how does such a model generalize there?
Yeah, a very good question. In fact, for few shot learning, what is the concrete number you mean? For example, 16, something like this. And in this case, in fact, we've already did some preliminary experiments. And in this case, type PMV2 or type PFNV 2.5 is better than typical, but they are still, in fact, better than the others. What means tree-based models? Yeah, they are still on the top of it. But what means that, in fact, at least currently, tabular foundation models are not very suitable for few shot learning. Yeah, maybe a future direction that we need to improve. Yeah. Thanks.
Yeah.
One question.
Yeah.
Is it applicable only to numerical data or also to text data, for example?
Yeah. In fact, we've already received feedback from different domains. For example, medical, finance, education. In fact, we are surprised that, in fact, tabular foundation models can just work well for different domains, even though during pre-training, we do not, for example, for the pre-training data set, we haven't specifically designed some prior to match the distribution of this domain, but it works. But what means that if you have a large amount of domain-specific data, you can just fine-tune it. It should be better. It should be better than what mean the general purpose typical. What mean fine-tune the typical V2 should be better than a general purpose typical V2 for specific domain. If you have a larger amount of the data, you can fine-tune it. Yeah.
Thanks for the talk. In your future directions, you mentioned like incorporating agentic system. Curious about what would be the natural way to using like agentic system on tabular data. Stability that's really more fast than
Yeah, good question. In fact, what means that agentic not for language, for tabular processing specifically. For example, you can just wrap typical V2 as MCP. In fact, I think Paradigm has already used it. Yeah, you can just use it. In fact, basically a wrapper to let the large model use it as a tool. Yeah.
I think more time later for discussions in smaller groups. So thank you very much for the presentation.
Okay.
Next one is Matthias.
Haben wir jetzt einen Folge?
Nee.
Okay, this is me. Hi, I'm Matthias. I'm from Dortmund, Germany, working as a founding engineer at Kumo. Did my PhD in Germany as well on graph neural networks and created phylogeometric. I don't know who knows this one, but it's like an open source library for graph neural networks in PyTorch. So we at Kumo, we love graphs. We also love tabular foundation models. So we looking into topics together. So thanks Q for giving this super exciting talk about TabICL. And today I want to talk a bit about how we can move from tables to relational foundation models. We have a bit of repetition in the beginning, but we are all working and interacting with structured data models thousands of times each day, in the sense that we have e-commerce graphs or finance graphs or social media, and they are all stored in a relational database, and they can also be represented or understood as a heterogeneous graphs. And so we are also making predictions, or models are making predictions for us thousands of times on these kinds of data, such as item recommendation, medical records, and so on. But previously, creating these predictive models is a slow and manual work, and hopefully people seem to assume that LLM seems to be a natural solution for these kinds of tasks. But I think it's kind of established knowledge now that these does not really hold. In the end, making a prediction on a database is not equivalent to a sequence, and LLMs are not designed or trained to predict on these kinds of tasks. And so we thinking we need some kind of relational algorithm structure, understanding of columns, column headers, data types, relationships, and so on to answer these types of predictions accurately. And so our goal here is to really train these kinds of data as structured as they come. And we want to pre-train a foundation model to predict on these kinds of data in a training-free fashion. So this has a lot of equivalence to what we know and love from large language models, where we have like a natural language prompt. It can also incorporate context, such as documents, related examples, and so on. Then it has this common sense in-context reasoning, and it gives us a text output back. But if we apply this pattern now and move it to something like a relational foundation model, what does that actually mean? So first of all, we have a set of databases that can be on different cloud data warehouses. And then we're not asking a natural language prompt, but we can understand it as asking a relational prompt. So for example, what does this customer actually purchase in the next week? And then we don't have this common sense reasoning, but we're having this relational reasoning. So we're reasoning over the history in this database to understand what the user cares about, its history, what other users in this database with similar transaction patterns bought, to give like a good prediction back. And so instead of a text output here, we actually get a prediction or an embedding back. So what are relational foundation models now? And what are the challenges? And so I think there exist three challenges. One is that we kind of need to operate on diverse database schemas. So we want to work in e-commerce, finance setup, in healthcare setup, and so on. So, and these databases all come with different kinds of schemas, column types, relations, and so on. And so this foundation model we are trying to train needs to adapt to arbitrary number of tables, columns, links. It needs to take this heterogeneity of column types into account. And obviously, we train against a number of these databases during training, but then we expect that this generalizes during inference to new unseen databases. So this is the data input part. Then we have the task type definition part. So we need some kind of definition of what we are able to query on this database. So this can be something like, what will the user buy? Will this customer churn? Is this transaction fraudulent? Is there a risk of hospital readmission? And so on. And these kinds of tasks all needs to be mapped to something like a machine learning problem, such as classification, recommendation, regression, and so on. And most importantly, we want to go beyond IID assumptions, beyond missing cell imputation. So we're really interested in temporal forecasting problems here. So we not want to necessarily just predict missing cells in our database, but we want to go beyond that and predict kind of the future. And then we need a model that combines this database schema, this data, and this task type definition into something that can process and do in-context learning over historical data. So we're kind of using the history that is available as part of snapshots in our relational database as in-context learning examples, and then we're using this to derive a prediction for the future. Most importantly, I think predictions are not the end of the story. We need to build trust in our model. We can do that with evaluations. So it's always good to verify that the underlying prediction we give to the user is accurate, and the user can trust that one. And certainly, I think it's super meaningful to think about something like explanations, because just the prediction alone doesn't build enough trust without a good explanation on why this prediction was made. And we kind of want to group all of this into what we call a relational foundation model. Some related work on RFMs. So I think this field in the graph learning community is around 5 to 6 years old. So people have been thinking about that for a long time. It all started with graph foundation models on text attributed graphs. And so the main challenge in graph machine learning was always that we have different database schemas and no one really know how to bring that into a single unified embedding space. And then people did go ahead and just said, oh, let's just textify all my rows in my database, pumps that through an LLM, and then I get like a single embedding back that describes this row in my database. I think this has, as we kind of know from this whole tabular foundation model revolution, significant downsides, such as everything needs to be textual grounded. There's like no good representation for numbers and so on. Then we have the tabular foundation models, which rely on in-context examples and kind of started this whole revolution, but they're kind of only working on single table. They have this IID assumption, and they kind of still require some form of feature engineering to bring your database into a single flat schema. And then we have the latest effort, which is we can use these tabular models and these tabular foundation models and bring them to the relational domain by building and engineering features on top of this database to kind of correspond to this single flat table prediction. So maybe you're giving this data set here of 3 tables and products, and you want to predict churn for this customer. And then you find yourself engineering features such as number of monthly orders, sum of weekly item prices, and so on. And then you can kind of bring this into this flat, nice schema here. The main problem with that is that all these features are chosen kind of manually. They are not kind of data-driven or engineered by a model. And only partial data is actually used. So we can only use all the features we actually engineered, but we don't necessarily know if we have all the meaningful features really captured. And then this just requires lots of back and forth. And so it's not really applicable for a zero-shot training-free model prediction that we expect to come up with in a second or two. And then based on this approach, we see a new trend, which is let's do automatic feature engineering on relational databases. And so 2 popular approaches just came out the last month, which is the RDB learn approach, where it says like, oh, we can do pre-aggregate all these columns in my subgraph neighborhood or in my local entity subgraph based on some fixed aggregations. And then I put that into a tabular foundation model. And I think this works surprisingly well, but you're ending up with gigantic wide tables now because you kind of need to aggregate everything into this flat table and to create examples where such an approach fails because you never really can learn pairwise dependencies between features far away in your graph. And then another GNN, so you're kind of using the subgraph embeddings of like a randomly initialized GNN that kind of pre-aggregates all this information. This works surprisingly well because the GNN has a natural structural bias. And then you kind of use this random but biased subgraph embedding and input that into tabular foundation model. And I think it's obvious that this kind of ends up with a blurred representation that can only get you this far. So our goal here is to kind of rethink that a bit. And I think it's important to think about training an actual foundation model that kind of has this relational structure in mind that is kind of trained end-to-end on these kinds of data. And so the key insight we have since 4 years now in Kumo that your relational database is a temporal heterogeneous graph. And so you can understand all your connections or foreign key relationships in your database as a subgraph around a specific entity. So we are looking at a single entity. We see its past views, orders. From the orders, we see their products. From these products, we see what other people have that viewed or ordered this product, and so on. And you can kind of go this recursively down very, very deep. And so in the end, you can also represent this as something or input this subgraph into something which we call a relational graph transformer. And so you can kind of understand this as a sequence with positional, with specific positional encodings designed. And the farther you go, the more information or the more collaborative signal you're actually getting. So if you're just sampling like the first 2 hops, then all you get is like the past interactions of this user. And then this kind of boils down to a sequence modeling task. But the real strengths here come into play when you go deeper and kind of get this collaborative signal in. I think this paradigm is super powerful because it exists means we can on this pictures. So we can last holidays or previous holidays and so on. So the transformer itself doing multi-head attention on this sequence can naturally learn such kind of look out for. Then we have correlations that we can see. So for example, items that have been bought together, we can see repeated patterns, regular patterns, certain trends, and so on. And then we can also aggregate that with softmax weighted average. We can do the summation, standard deviation on top to learn these kinds of different aggregations and patterns over a single subgraph. So this is like the principle of relational deep learning. Now we want to bring this principle of in-context learning and marry that together with relational deep learning. And this is actually following a super similar setup than to the tabular foundation model setup, but we're not inputting single rows as our in-context examples. We're actually inputting individual subgraphs. So that means, and most importantly, we're also treating this as some kind of temporal setup. So that means we have an entity E at timestamp T. We want a prediction which is graph around entity E. And then we sample a set of context subgraphs and their ground truth labels from an earlier timestamp. So we have this T hat here, which is lower than T. That in our database, and since we are in the past, we can also gather the ground truth labels. And then we combine this information into a unified architecture to make a prediction. So we are sending this prediction subgraph in, and then this pair of context subgraph, context label over all different in-context examples, and we input that into a flow. So we kind of started with this effort in May, that was the point where we released our first version. And we're actually about to release our second version of Kumo RFM, which is, sadly not yet here in 2 weeks. I'm sorry. But this is a model that is trained on both synthetic and real world data. And we kind of tried to understand what our version 1 is doing and kind of, eliminate all these kind of child diseases from it. And so what we found out is that our V1 version is like an expert structural learner, but it's a junior feature learner. And that means that it can reason over structural patterns such as recency and so on very well. It kind of fails to be a good feature learner. So in itself, it's not a good single table model, for example. V1 can get very confused if the number of tables and the number of feature column grows. So it doesn't have a natural way to kind of destroy, eliminate irrelevant tables and columns from our subgraph. And then V1 cannot differentiate between local and global context. And what I mean by that is we input in context examples into our model, but we don't know, or the model that has no natural way to understand, oh, this is an entity that is the historical subgraph of myself, of my own prediction, or some unrelated global entity I have input into my context as well. And so we're kind of trying to fix all of this in V2. And so we're giving table level features much more importance here than just structural information. We inject label information as soon as possible. We increase our training data to kind of get rid of these effects. And then we have a smarter context sampling strategy to kind of eliminate these artifacts here. Predictions. I think that's confusing. In the end, what we're doing is a quadruple hierarchical attention, which sounds super fancy, but it's actually hopefully pretty straightforward. So what that means is that on every table, we're kind of learning a good row embedding or node representation. Every row in our tables is a node in our subgraph, and we're trying to compress that or learn a good representation out of that. And so what we're doing here is super similar to tabular foundation models in the end, which you can also describe as like a mini in-context learning module. And so we're doing table level column attention and table level row attention interleaved together to learn like a good representation for each row. Most importantly, we're injecting these context labels already at this stage so that every row kind of can learn that learn a good representation and kind of discard irrelevant information that is not specific for this kind of task. And then afterwards, we're having like these node row embeddings, and we can apply a second interleaving here our graph transformer attention, which exchanges information within each subgraph. And then we have our context attention that exchanges this information from the graph transformer module across different subgraphs in our in-context examples. And that's it. So I think it's still hard to understand what these foundation models are actually learning or doing. I think there exist many different ways how to describe that. I think this is my view on it. So in the end, what this model is doing in a single forward pass is it looks at and relates column-wise feature distribution. So it kind of learns how values are distributed over columns within each subgraph and across different subgraphs. It learns and relates interaction patterns across different tables, such as recency information, neighborhood count, and so on. And then it relates these information across different. Very important to understand that this is not a foundation model that has kind of world knowledge baked into it. And so if we think of LLMs, we know these are trained on terabytes of data from the internet. And so they have this world knowledge and so on. But here, model in foundation model and so on yet. This is mostly due to the reason that we don't have sufficient number of training data available to train such a model. I think we now scraped every publicly open source relational database from the internet, but there doesn't exist that many. And so in the end, we're trying to build a foundation model here that is able to reason and relating over this data in a single forward pass, but it kind of tries to infer what a relational database is on every forward pass. And so you can actually think of RFMs as performing supervised optimization on the fly. I think that's my take on that. And so how is that actually trained? This is trained in kind of 3 stages. We have the table level structure causal models. And so we want to make sure that our relational foundation model is also a good single table learner. And so we can inherit all the learnings from the tabular domain there. Afterwards, we move to the graph level stage where we synthetic approach, which we put on archive, and where we kind of see these scaling laws of synthetic data and training. And then lastly, we fine tune on real world data, where we have like 200 open real world databases, and then we're generating about 1,000 tasks per database across all different timestamps. So this, in theory alone, gives us very much training data to use here. We evaluated Kumo RFM on different sets of database. One is the RelBench one, which comes with 38 predictive tasks. There's this cool new data set from SAP, which is sales auto-completion. And then we have the 4DB infer data set from Amazon AWS. And we compare against different baselines here, such as relational deep learning supervised approaches, tabular foundation model, the data that is asked to solve each task with manual feature engineering within a day. So this is like a super dense table. We don't look too long at it. And so here is that we kind of see that Kumo RFM v1 and Kumo RFM v2, we see a big bump in improvement or in accuracy here. What we also see is that just using something like LLMs to predict, just look at the average AROC here, is not sufficient to answer most tasks sufficiently. We also see that something like other relational foundation models are kind of underperforming on this benchmark. And then we're seeing that the data scientist baseline, this manual feature engineering, is still super competitive, but still loses out on these relational foundation models. And what we see last is that once we start tuning or fine-tuning this model, we kind of see, so we only have fine-tuning for now in V1, so this data is a bit mixed up. But what we see is that on small-scale data, we see that Kumo RFM V2 has kind of overcome here and even improves specific fine-tuning, while the larger the data gets, we still see massive improvements from fine-tuning, which I think makes intuitively sense. So we can see similar patterns on other data sets, such as entity classification, entity regression. We see in general Kumo RFM v2 achieves big jumps here. We also see that on other tasks where we have, for example, recommendation and missing cell imputation, but in particular on the recommendation task, I think that is the one that requires the most attention next, is that in particular fine-tuning can really boost the numbers massively up here. Lastly, I want to quickly talk about the whole vision around this project, because it has been a wild ride, and it's not necessarily just about the model, it's about the experience and how to use these predictions and turning them into some form of dialogue. So how we envision this whole project is that you can kind of connect Kumo RFM to a relational database via a semantic model that defines primary keys, foreign keys, time columns, semantic types of columns, and so on. Then you can start asking question database. And you can do that, for example, with our in-house built predictive query language, which is inspired by SQL, but designed to answer questions for the future that can be then mapped into like a machine learning task. And so this naturally supports something like missing value imputation, something like aggregated future behavior, churn, LTV, and so on. And then you can also predict something like future links by saying, list me the distinct item IDs of orders the user does in the next 7 days. Then we can use this database and this predictive query definition to fully automate this whole process of in-context generation, because we have all we need in order to generate prediction subgraphs, in order to generate because this definition here alone tells us how to generate labels by going back in time and then looking ahead. We can pipe that through a model, and then the main goal is how something that guides a certain decision. I briefly mentioned the explanation part a bit at the beginning, but RFMs are fully differentiable, and so they naturally enable something like gradient-based explanations. We can compute kind of importance scores on the cell level. We do some more tricks on our end, so we're not only generating cell level importance scores, but also subgraph level or in-context example level data statistics. And then we can have this textual summary module that kind of relates these different statistics and outputs together to come up with a good explanation of why a certain prediction was made. And lastly, we also see that not as something that will replace LLMs, but it's actually an additional tool in order to make LLMs much more useful. So you can think about that as integrating this whole set of Kumo RFM as a tool as part of an LLM agent or chatbot, which you can just query with something like what sales closed last quarter. So this is like a historical query. So we can route that to something like a retrieval engine, SQL-like tool that gets this information from the past. But whenever you ask something like something that requires actual predictions, it would route something, this query to something like a prediction engine, maybe something like Kumo RFM. And most importantly, this retrieval engine and this prediction engine, they would work on the same semantic model, so they would be totally consistent. They can be stacked and composed together to answer more and complex queries altogether. All of this is kind of testable and usable with our Kumo RFM SDK. So for example, read in pandas data frames, construct a graph out of that, query this with something like predictive query. We also have an MCP server. You can directly connect to something like Cloud Desktop and start talking to your data. And then the last thing I quickly want to talk about is that this can actually scale to terabytes of data. And what I mean by that is that all this subgraph sampling and label generation computation can be actually pushed down to the data warehouse. So what is that we can, for example, connect Kumo RFM to Snowflake with the Snowflake connector API. We can also connect to something like Snowflake semantic views, where you can have additional views on tops, columns, expressions, and so on. And then all this computation that requires data from the data warehouse can be actually now pushed down to this exact data warehouse. So we can infer the metadata from the database schema. We can infer subgraphs by performing recursive SQL statements over the set of entities. And then we can also generate labels by using something like a predictive query to SQL mapping. And this gives us now a way to basically scale infinitely to any number or any scale of database. We personally tested that on 300 billion rows. It works just fine. Where to go from here? I think, there exists many different ways. I think you mentioned a lot of what is also written down here. On our end, I think context selection is the main big blocker. So we are talking about application something in context examples of size tens of thousands or 50 of thousands. And so there's like a mismatch of what data is actually available and what data we are actually using as input to our model. The current solution seems to be just brute forcing and increasing the context size. I think you can do much more elegant here by finding a better context as you go. The one thing that also keeps us awake at night is how can we actually bring something like semantic world knowledge into this model to make more accurate predictions. We want to go beyond something like simply classification and regression. I think having a better recognition model is these are all tasks that we kind of want to solve with Kumo RFM as well. Something like text representations, I think, still remains a major challenge even for tabular foundation models, because these tables become so wide when you just use something like a text embedding on its own. The one thing that is super challenging on our end is like finding the optimal. So on that, it is fine granular to answer a predictive query in a very good way. So oftentimes we're working on the level of individual transactions, but then the actual prediction task is something to predict the number of items, item sales in the next year. And now you're looking at 1 million, tens of millions of transactions you need to aggregate from this item set. And I think that's something that can be solved by semantic views and agentic workflows on top, which kind of goes against our principles of no feature engineering, but this is the world we live in. And then what is also worth pointing out is that there still exist a few hyperparameters in Kumo RFM that are always worth tuning. And so I think the most important one is the sampling depth, like how far away do we actually look into our subgraph and what do we input into our model. And it's kind of impossible to know in advance where the signal lies in our subgraph. So there's prompt engineering required, which can be resolved by something like a thinking mode that goes off for a minute and comes back with like the optimal solution. I think something like fine-tuning will stay at least relevant in the near future, just because we don't have a way to scale these foundation models yet to large scale data. This can be on different levels. We could just imagine fine-tuning on the schema level or database level or task level or everything all at once together. And then I think just related to deciding an inference side. And that's it. Thank you all.
Yeah, I have a question.
Oh, okay.
Yeah. So again, I'm quite curious about the inference latency. So for example, if I understand correctly, for each query, we need to perform context selection. So, but in practice, if you have many thousand queries, this process, so that you can, for example, make full use of GPU and in fact, how do you do it in practice?
So it's important to understand that this is like a two-stage process. So this whole subgraph generation, in context example generation, that happens either locally or in the data warehouse. And that is then the output we receive of that we input into the model. So there's like two different levels of concurrency here.
Do you see a future where the tabular foundation models are like small models trained only for a particular vertical, right? Because if you train a huge tabular foundation model for health, finance, and so on and so forth, and if I want to just use it for my finance industry, it doesn't make sense.
Mm-hmm.
And I see the fine tuning that you have, it makes sense, but sometimes fine tuning makes the model even too narrow in its thinking, right? So where's the My point is like, where is the future heading? Do you see like smaller models for industry, or just like one generalized model being used across the industry? So I'm not Kumo, so I cannot predict the future. So I think in order to go for different verticals, you need to have something like semantic world knowledge, because otherwise you will always benefit from more synthetic data, larger models to improve on a certain vertical. I think that would be my current opinion on that. Oh,
yeah. From the previous talk from Kumo, they are saying that this relational foundation model filling the holes of LLMs, right? In critical sense, but LLMs are really good at summarizing the given text. So if I have given this, how relational foundation models can be used to summarize the understanding how the business is working.
Is that a question? Shall I just comment then? So I didn't want to bash on LLM. I'm sorry if that appeared that way. So I absolutely love LLMs. I think they're just not designed for these kinds of tasks we are interested in, right? If you want to ask the LLM about an item recommendation, that's not really possible. And if you ask it about whether a user will churn, it's also not possible. And you cannot ask it if that transaction is fraudulent. So it's just two complementary things that can be stacked and composed and used together to build something much bigger.
But yeah, I feel like relational foundation model could help even better. In data sets and get a summary.
You mean as some form of RAG solution, or what do you mean?
I don't know what to like. The thing is to understand the business from the different tables we have.
That is true. Yes, I would agree with that. Yes. I think.
I really like that your operator is kind of part of the optimizer by a Snowflake, where you push down the operator, the semantic operator, which inside the model. So I was wondering that if you fit the model in a database system which doesn't inherently support semantic operators or doesn't have the optimization by pushing down, so there you might have some problem with the scalability of when you're applying the model on billions of data. Is that a problem you think, or?
I mean, if you're operating on a database level, you can always push down any data relevant compute, yeah, right?
The optimizer has to be able to do it for you, right? If it's part of a larger query.
What do you mean by optimizer?
Example of a query where you use a SQL operator predict, which you connect to Snowflake, and then Snowflake understands it that this is the query that does the inference for a model which exists somewhere, and then this is down in the query tree.
I mean, you're referring to this one? So in the end, that means you can initialize a Kumo graph by connecting to a database, right? And so this would give you now a graph that has foreign key links, primary keys defined, and so on by reading from the database schema. And so there's literally no work we need to do here, but in the predict call, we need to create the in-context examples, the labels based on the query, and we need to input that into the model. And the first two we can push down to the database.
Time for one more question.
Yes.
So we mentioned always causality and explainability. To use these models, that's a big segment. So what's your take on implementing causality and explainability in the end-to-end prediction?
I mean, we have explainability as part of this. We haven't thought about too much about causality yet. I think that will follow soon. There exist some ways you can formulate that in predictive query already, but it's not like a fully fleshed out solution. On the explanation part, we're using, as I said, these gradient-based explanation techniques, these global data analysis, and then we're trying to give like a good explanation by having like a textual summary on top, which a user can easily consume.
Thanks a lot, Matthias.
Super, thank you all.
Mia?
Hi. Can I start?
Yes.
Very good. Graph neural networks, message passing. Just pass it on if you don't like it. I have one of these. I'll explain in a second. I mean, the message passing was just an analogy. I generally want you to drink this if you want, of course. If you don't want it, just to pass it on. It's only me standing between you guys and sandwiches and drinks, so I said at least I can give you drinks in advance. But also there's a specific thank you I have to give to all of you for coming and showing up, because at Kuma we're in the business of predicting the future, right? So of course today when we were sitting with our colleagues, organizers here at lunch, what we did was like, let's predict how many people will actually show up, because there was like 120 plus of people applying being accepted in there, but you know, not everybody always applies, not always show up. So I said, okay, let's see how many they do. And I'm an optimist, so I went for a high number. Let's just say we're not there yet. Why is this important? It's because, you know, we need to train our people to predict well. So we give laws and we give a gradient descent on that, right? So basically, we need to punish them if they're wrong. So everybody that got a wrong number will have to do push-ups. And how many push-ups? Depending on how wrong they were. Basically, for me, that means everybody of you showing up here, one less push-up for me. Thank you. Did you manage to open it? I had one opener, so you have to share that as well, unfortunately. Is there an opener? Yeah, you're around. So make sure you find the opener. Anybody else want some more? Okay. While you're working on this, so we had Fede, we had Ramona, we had Katie. Where are you, Katie? Katie, me. I didn't win. And we had Matthias. What do you think? Who won? Time for you to predict. Who's in for Katie? Hands up. All right, we got a couple of them. Who's in for Ramona? 1, 2, 3, 4, 5. Who's in for Matthias? He's a smart one, eh? Yeah, the most hands. Who's in for Fede? No, almost nobody. Fede got it like almost exactly. I think ±1. So he can be lazy. Anybody else with the water? Yeah, well done, Fede. Yeah, sure. Otherwise, there will going to be drinks later on as well, so don't worry about it. All right, that was the intro. I also do coding, not just talking and amusing people. How do I go on? Very good. So yeah, Micha Pilko, ML engineering at Kumo, joined about 3 months ago, which, you know, Newton has said, if I saw further than others, is because I was standing on the shoulders of giants, or something along that line. In my case, I'm not even seeing further than the others, right? I'm just kind of going to the giants, poking them and saying, guys, what are you guys doing? And you know what they tell me is what I'm going to show you here a little bit. So we're working on infrastructure at Kumo, and Matthias has kind of touched some of this. I'm going to be touching this a little bit more. Today I'm going to talk about Graph Engine. Again, kudos to Zach, to Min, to Adi, to Vedant, all the people who were really contributing and putting this together. It's something we have in-house, and it's the Kumo's high-performance graph backend. You were mentioning before about the scalability concerns. That's part of what features in there. So Matthias told you everything about graphs and how they fit in. Well, oh yeah, you can see this. Great. So you can imagine, right? So very shortly summarized tables, relational databases. And you need to feed that into the PyTorch data loader for training or for predictions. And what graph engine is the thing that sits here in between. I can already tell you in the beginning that what graph engine does as a part of it is it produces an intermediate representation, materialized representation of the data that's not, that's already considering the graph forms, so basically has graph semantics in it, and it basically then serves that further on. So why going for the custom backend? I mean, your question was a little bit answering that. Matthias was telling us, right, we can do, for example, on Snowflake, we can push down compute, and that's great. We can do sampling with Snowflake. In that sense, that's kind of great, but it does have some limitations, right? So one thing is we don't only have customers that live on Snowflake. There's Databricks. You can also push down there. There's others. But in one way, we can, if we have our own solution with own internal representation, we can kind of centralize that. We have like a single point from which we can build on, also then for the sampling size, right? Making sure that that really works well. So that's one reason. The other reason is, and yeah, why we want to have it is we need to have this fast sampling. Koen was mentioning before, I mean, they're making the models really go boom, right? And then all of a sudden, the bottleneck is no more the model itself, it's just kind of feeding the model. And that's, for us, that's sampling that really feeds in, right? So we need to do this sampling. And so our internal representation of that data needs to be set in such a way that the data layout is optimized for that sampling. So a couple of things I've written there, like a fused node features. So basically we have indexes of nodes, indexes of edges, and we have these features of the nodes that are basically then fused in there, and just helps us to do sampling efficiently, and at the same time also pulling out the features of the nodes that you need. Finally, what we're really seeing in the customers is, and that's maybe a step before that, is when we're going in a Kumo enterprise solution, we also do custom model training, right? So today we mostly talk about RFM, so pre-trained relational model, but we also have this training. And often it's not the training of those custom models that is the bottleneck. It really is the preparation, the data prep time. This really dominates the whole, the end-to-end time of getting towards a model, right? So we really need to be careful also when we are going from customers' data onto that internal representation, that this is really efficient, right? So now if we have that system that we own it end-to-end, have a single solution, then we control this, we can really optimize this as well. And that is part of what we do with Graph Engine as well. So this is the first part, right? So in a way, if we go back and see what Graph Engine does, it has kind of, you can see two stages. Ingest stage, so creating that representation, and another stage of sampling and serving of that, of subgraphs from that representation. So the ingest is the first stage. You have source tables from different places. We mentioned Databricks, we mentioned Snowflake, raw Parquet files, any much as possible. Then you can sometimes use databases or semantics on the databases to infer the graph schema and graph configuration that Matthias was mentioning before, or sometimes you have users define that themselves, right? Define the structure of how the tables connect to the other tables, primary foreign keys and whatnot. So you give this together, and then the machine Graph Engine goes room, and it creates that internal that representation, which I mentioned before, consists of node indexes and edge indexes, with compressed features into those indexes. And another thing to mention here, it's this whole thing is sharded. So this sharded kind of let us parallelize the actual representation. A couple of things. One is it lets us parallelize it. It also lets us compress things a little bit better, because we can do compression per shard, which just basically makes the whole thing more efficient, both in time as well as in memory and in space. One thing I forgot to mention before is this internal representation or intermediate representation sits on disks, SSDs ideally. So it's not just in-memory representation, it's really material efficient. There's also metadata next to it. It's mostly statistics that is useful for down the stream for encodings and whatnot. Right. Okay, so this was, I forgot to refresh. So this was the first part, creating that representation, and the second part is now sampling and serving subgraphs, which are our rows from that representation. I think Matthias again explained this a little bit already, how we do it. This is a little bit more in detail. So if you remember that picture that Matthias had with the user and then the product and so on and so on, right? This is, you can see it here turned around. So on top, what you would call are the seeds, right? The users. Here there's a product level, and then this is the transaction level. So you have this hops that we call them, that are being called, and you can define how many, the depth we were talking about, how many hops you do, what's the fan out that you do on each of the hops, and those will define your subgraphs, right? So besides the fact that the nodes in the graph are heterogeneous, there is also a temporal part that you need to consider. So what we try to do is, already in the intermediate representation, we lay things out in a way such that we can do layered sampling. And then the temporal sampling becomes quite efficient now. So a little bit here more into the details. For example, what you do is you do batched sampling. So you don't just go for user per user, like a for loop around user per user, but you do this in batches, right, of several subgraphs. Second is you go layer by layer, and then because of the memory layout on disk of our internal representation, that becomes more efficient to extract the edges and the features from it. Another thing you do hop deduplication, so you don't have to kind of read the same node several times. If it's being reached through several subgraphs, you can only do it once. And then we do cross-shard grouping. It's another optimization for making sure that we're hitting indexes that live together on disk, and as such, being more efficient. So this is a little bit more in details, right? The things that are used. Try to do as few memory copies as possible. So we do memory mapping with I/O on the files on disks. Well, that's let us basically use OS, like Linux kernel, to manage the hot data that can do smart prefetching, right? This is where it's important that we go layer by layer, so that the kernel knows when to prefetch that data when it's memory mapped. So we can get better performance there, and we have basically zero copy file access. Then the other thing is vectorized unpacking. If you're more on the data science side, you're always told, right, don't do for loops in Python, to go NumPy. That's pretty much what there is, right? You can make sure that you use the SIMD, so single instruction, multiple data instructions on the chips. So like in our cases, the edge parsing is able to do that. So we have this decoding in vectorized fashion. And another thing that's important there is like a lot of things are compressed. I haven't talked about it yet, but basically everything is compressed. The indexes for the edges are compressed. The features themselves are compressed in a rollback fashion. So this one specifically speaks about the feature-based compressions that happen, and all of those things, they happen at ingest time. So when we're ingesting the first part, this is where we redo all the statistics, computation, and so on, so they can do this efficient ingest. What lets us then in the decoding part to do kind of this zero decision decoding, right? So you have everything pre-computed, all the decompression constants are there, right, so to speak, right? So you can really optimize you really optimize for the read base. Let's put it that way. Right. So finally, okay, you've now sampled those subgraphs. Now you have to somehow serve it to PyTorch in our case, most often. And then we have kind of two ways of doing that. Reason one is, main reason is, if you can do it in a single node, right? Your SSDs are where your GPUs are. That's what you want to do, right? You have, and then that would be like the preferred path. But sometimes the whole data is just too big, so you might have to serve it from a different node, and for that we allow for Aeroflight delivery system as well, gRPC streaming of those batches. So yeah, that's pretty much it of what we have there. Now some numbers of what we're able to achieve with that is, if we're now in the single PyBind direct single node, we can always start scaling up vertically, like the number of rows. You see the numbers there, like billions of rows, up to 500. Depends a little bit, of course, on what's the actual table sizes and features and so on. But we can cover dozens of terabytes, have a pretty decent sampler bandwidth, and hopefully put the pressure back on the guys actually, running the model, that they get their models faster. So basically this is my daily battle. Can I Okay. Can I blame them for being slow, or will they blame me for being slow? That's pretty much it. Yeah, and that's it. Thanks. Who else?
So I'm wondering why do you have to visualize the normalized intermediates in the disk? Can you not directly stream from the source to whatever you need to?
You could, but what you typically want to do, like for example, you do fine tuning, right? So you have this graph structure. You don't want to always recreate that graph structure. So you want to have that intermediate presentation so that you basically you do one materialization and then you do continuous sampling from it, right? So yeah, so it's basically for that reason.
On the compressed representation, or you have to decompress it before you.
Depending on which computation, right? So there's some. Now I have to think the details. So we do have a O1 lookups to find the information and directly get it from the memory maps, right? So that's important bit. And for that, there's no decompression needed. Now, then once we have the features out, then you have to decompress. So, I mean, what goes into the graph then is decompressed. So we don't do, well, at least until now, I don't think we do, training on the compressed data. No? So so they have their own ways of doing encoding. So we let them encode the features in their way.
Okay, otherwise there's one.
No, they're sandwiches. That's what I'm.
Yeah, otherwise, let's get to the networking and discussion part. You're welcome to join for sandwiches. Again, a reminder, we are hiring, so feel free to scan the QR code for open positions. Then, yeah, we can also show the QR here.
Sorry, yeah.
Coming. Thank